Yeah. Let's continue. We were looking on the directions, 3 current direction in primary case, and in which partial circle some partial directions. And we are comparing. For example, if we want to find the value I1, then we have right direction from the left to right in the initial circle, and in first partial the direction is the same, and in second partial the direction is opposite. Then it means that we have to take current I11, here it is, with plus, but current I13 with minus, because this green direction is opposite to the primary one. It will be current I1. Then the same for other 2 currents, I2 and I3. For current I2, all directions are the same, as we see, and we should just add each partial current in each situation. And the last one, in first partial circle, we don't have current because of open case, and just plus partial current in green circle. It will be the same as in the initial one. That is how it's works. Just what I want to mention, that we should be attentive to the direction of partial circles, because sometimes it could be minus depending how it compares with the initial mathematical model, initial general case. But after we divide on 2 circles, we just calculate them separately. In first circle on picture number B, we have only one current direction, only one loop. Only one loop, and it will equal electromotive force divided on 2 resistivities, E over R1, R2, it will be 0.67 amperes. The last current equals 0. Both current I11, I21 the same, 0.67. And we solve the picture number B. For the voltages, just one moment, let's have circles. Let's have circles near the eyes for the whole time. Here they are, just to see them.
Professor.
After we find, I
have a question, please.
Yep.
In the
Yes, please.
in the second picture, How did we know that from where do we
Picture
start the
C.
direction? C, yes. From where do we start the direction?
Generally, we choose the directions but by ourselves, but we know that current direction J from the source goes up as the arrow direction. And because this current 3 had the direction in upper, then it will divide on 2 different branches, just like here. That is how we know direction. Generally, we could choose direction as we want, but physically, if we look on the circle, we know that if current source makes some currents in the direction, that it will just divide on 2 other branches.
Okay, thank
you. Yeah, welcome. Welcome. Maybe any other questions? Okay. Okay. Then after finding current in case number B, we can find voltages just as multiplication current on resistivity just from the Ohm law. And we see that these 10 volts in circle number B divides as 6.67 and 3.33 volts between 2 resistors in the left part of the circle. It is a first partial model. The second part of this circle, it is represented here from the current source. We could find the partial currents in case of resistor R1 and R2, or from voltage, or from proportion between 2 resistors. We could or find voltage as current multiply on parallel connection, as it's shown here, and then voltage AB divide on resistor R1 or R2. But the same, in the same situation, we could just use proportion, because in the higher, if we have 2 parallel branch and inflow current, it will divide between 2 resistors. In higher resistivity will flow less current, in less resistivity will flow higher current, and it could be found just as reversed proportion as it's shown here. Both of these calculation, first or second, could be applied and gives us the same numbers. Current I13 0.33 and current 2.1, or it should be 2.3 as it here, just a mistake on the picture. It will be 0.67 amperes. After this current, we could find voltages. Voltage about 3 volts per each resistor. It means that voltage AB equals over 3 volts, approximately 3.33. And after we do it, the last step, we just add in currents and voltages to obtain the solution of our starting task. First current in the left branch, because of different direction, one current we're taking with minus and obtain 0.33 amperes. The second central branch, adding 2 currents, 0.66 and obtaining 1.33 amperes. And the last one, only one branch with current, because in case number B, it disconnected and it equals 1 ampere. And as we see this, let's return to starting circle. As we see, we have 1 ampere here, and 0.33 amperes here, the left branch, and 1.33 in the central branch. And we could check that everything solved correctly, because according to the Kirchhoff law, 2 inflow current should equal outflow. And if we will add 0.33 and 1, we will get in sum 133. And because these 3 values was found independently, and then they are checked by the Kirchhoff law, it means that everything was found correctly and our solution is right. The same about voltages. We could add voltages on each resistor depending on the direction. For the first resistor, 1 voltage has opposite direction because opposite direction of current, and we obtain 3.3 volts. And on the second resistor, R2, in total, we have 6.6 volts. After adding, we are obtaining 10 volts of total voltage on both of these resistors. That is how it is used, but one restriction about values, that you could use superposition method for currents, for voltages, but not for powers. You cannot find power in one case, power in second case, and then just add them, because power is a non-linear function. Power is a quadratic function from current or from voltage. And you cannot apply superposition theorem for a quadratic function. You can apply this theorem only for linear functions. That is why only what you can then use the total current and total voltage in the primary model and find power only in the primary model, the primary circle, the total circle of your task. But also that's okay. If we want to check the power balance, for example, let's return to solution for currents and for voltages. And we could check power balance. We see that current equals 0.33, 1 amperes, then 1.33, 3.3 volts on the first resistor, and 6.67 volts on the second resistor. About consumers, power of resistors, it should be I1 square on R1 plus I2 square on R2 let's check what it will be. 0.33 in square and multiply on 10, it will be 1.1 watts. plus 1.33 in square multiply on 5 ohms, it will be 8.8 watts. The total power consumption equal 9.9 watts. And about sources, you have two sources of energy, electromotive, multiply on current I1, and current source. Current source, you have to multiply on voltage AB between these 2 points in which this source is applied. Multiply on voltage AB. Electromotive 10 multiply on current, you have 3.3 watts, 0.33 multiply on 10. And for current, you multiply in 1 ampere on the voltage. Voltage equals 6.6 or 6.7 volts. And as you see in total, you also have 10 watts of consumption. Then you see the power balance and see that also our solution is correct. But the main restriction that we should calculate power balance in total circle, but we cannot find some powers just adding powers from partial circles, only adding currents and voltages. It is a single restriction. Textual summary that we discussed by words, you could look it through by yourself. And the next example, just let's see it shortly, how it could be applied on the situation of two electromotives. The same idea that of electromotive and current source, you are dividing the circle with two electromotives on two circles with only one electromotive in each of them. First circle, when you E2 substituting by 0. The second circle, when you E1 substituting by 0. Then you obtain circle with only resistors. You could calculate the total resistivity of this circle, just R2 plus R5 in serial, then parallel to R3, then in serial to R1 and R4. The total resistivity almost 17 ohms. And after it, voltage could be found voltage in central branch, and from this voltage could be found everything else in this circle. Then could be done the same with E2, but resistors start adding from the left branch, starting from R1 and R4 in serial, then in parallel to R3, then in serial to R2 and R5. About 14 ohms total, and also could be found the voltage in central branch. After that, the total voltage from two partial circles adding, and the total voltage in central branch, here it is, on the resistor R3, the total voltage equals 25. And after that, only for total voltage, we could find a power consumption as 31 watts. It is just a second example, the same idea for superposition method. And you could use it on any circle if your resistors is given by numbers, is given by constants for linear circles, and independently on the view of energy sources. The energy sources also could be mixed, not only direct current, it could be some combination, for example, of direct current and sinusoidal current sources. Just like that. Please, if you have any questions, welcome on these methods. If no, we will go further for the equivalent generator. For this method, is everything okay? Is everything clear?
Yes.
Okay. Okay. Just if you get the main idea, it's our main goal for this lecture, just to get the main idea what to do. Because if it's the main idea is clear, you always then could substitute mathematics and obtain the appropriate number. Somebody will do it quickly, or somebody will do it more slowly, but if you get the main idea, everything will be okay. Okay, then the last one about equivalent generator method. It means that instead of some complex case of active circle, it means the circles with generators inside. You could simplify it and substitute the simplest case of generator only with electromotive force and equivalent resistor. Previously in our lections, we see a couple of idea of transformations that instead of two serial electromotives, you could substitute single electromotive as adding of these two values. Instead of current sources parallelly, you also could substitute only one current source as a superposition of them. Then we could substitute instead of voltage source with resistivity, also current source with resistivity, just recalculating the current rate inside this source. Always we could do such substitutions. But for now, for equivalent generator case, we are looking on this situation. Other way of simplification for our electrical circle. If we have some complex case, some circle with lots of elements, it could be any type of connection. I just drawing something, some type of connections with couple of sources, couple of resistors inside. It doesn't matter how it looks like. Some complex case. It could be lots of numbers. For example, thousands of elements inside. But if we will look on this circle as such called two poles, as a circle with two points of connection, then we could substitute this circle as a simplest equivalent of one single electromotive and one single equivalent resistor. It is the main idea. Instead of complex circle that you are looking on near 2 points, you could substitute as an equivalent one, also only with 2 points. This circle or this circle is called two poles because it is some mathematical model with 2 points of connection, 2 poles. Or it also could be called just a terminal. Some circle with 2 points of connection. If inside this circle only resistors, it's called passive, and it could be substituted only as equivalent resistor. If inside this 2 pole is not only resistors but some sources, it could be a couple of sources, it calls active and could be substituted or as electromotive and equivalent resistor, or as current source and also equivalent resistor. But for voltage source, resistor is connected in serial, for current source is connected in parallel. But you could substitute and find this simplest equivalent circle for any active 2 pole. And it's called the Thevenin theorem because of person who proposed this method. The circle with electromotive is called Thevenin circle, and the circle with current source is called Norton circle, also because of name person. And but they are equivalent between each other. The representation of theorem, it tells us that any electrical network with 2 output terminals with 2 points may be replaced with a generator that is means simplest circle with voltage source and resistor, and a series resistor without changing the current in a externally connected load. It means if you have 2 terminal system with complex case inside, you are connecting some load to these 2 terminals and finding current through the load. This current won't change if you, instead of active 2 terminal, will substitute the simple equivalent circle for generator. It is the representation of such called Thevenin theorem. Then how it works? Let's see some example how it could be transformed. For example, here we have some 2 terminal between points A and B. These 2 terminal consist of 2 resistors, 1 voltage source, 1 current source, and we want to substitute it by the simplest model, like here. Only 1 voltage source, only 1 resistor. What should we do? We should find the voltage between points A, B, and the value of voltage between points A, B. It will be the value of this equivalent generator. And we have to find total resistivity between these points, between points A, B, and the total resistivity of whole circle. It will equal the resistivity of generator. How it could be found? Let's find first of all the voltage between points A, B. It could be found using the nodal potential method. If you remember, if we have 2 potential points, phi and some 0 point, some ground, we could find this potential by the potential method. We discussed it in the first lecture. According to it, we are adding inflowing currents from the source to this potential and from the electromotive force to this potential, and divide on conductivities of all branches. Conductivity of first branch 1 over R1, conductivity of second branch 1 over R2, and conductivity of last branch is 0 because we have current source. After it, we found voltage AB. After substituting all values from the initial data, we found the voltage AB 12 volts, and it will be electromotive force in our electrical circuit. It is first part. The second part, how to find resistivity. Here is 2 ways of found resistivity. First, we could disconnect sources. Instead of current source, we could substitute infinity high resistance, and instead of voltage source, it will be 0. Then we get only R1 parallel to R2, 2 parallel resistors. First equals 1.5 kilo ohms, second equals 3 kilo ohms. If we will take them in parallel, (1.3) multiply on 3 and divide on 1.3 plus 3, 2 parallel resistors. It will be almost 1 kilo ohm. It will be 0.9 kilo ohms. Let's check it. Number 1.5, not 1.3. 1.5 on. It will be on 3. Yeah, it will be just 1. 1.5. 1.5. It will be just 1 kilo ohm, as it's shown here. And that is mean instead of circle on figure 9.7, we could substitute the circle on figure 9.11, only one voltage source 12 volts and only one resistor 1 kilo ohm. Simplifying initial circle into this one, and it could be done for any circle view. Even if you have thousands of elements, you could be simplify them using the Thevenin's theorem. Next time we will see a couple of situations using the different working modes of 2 poles, different working modes of these 2 terminals. How to transfer maximum power, how this power depends from the resistivity, couple practical situations. And after it, we'll move to repeating of alternating circle, alternating current, repeating of sinusoidal sources of energy. It will be our plan for the next time. And it is almost all what we discussed before the break. And then we will just continue the regular lectures about sinusoidal currents. For today, generally, that's all what I want to discuss. Please, if you have any questions, please welcome about this material.
Will you send us this lecture?
Yes, of course. I will add it to YouTube playlist, the link that I sent today. It will be a regular link. All our lectures, I will just add to these YouTube channels.
No, I mean like
Okay.
a file, PDF file.
File. File. Yeah, of course. File you already have on your on our Telegram group, I think. Here, there. Just one moment. Files. Yeah, here it is. In our group, in files that I sent, you already have it.
Okay, thank you.
Okay. Welcome. Any other questions, please? Okay. Okay. Then thank you for your attention. Wish you a nice day and see you the same time, 9 a.m. the next week.
Thank you. Have a good day.
Good luck and see you.
You too, Professor.
Thank you. Thank you very much.